Section 7.3, absolute value equations. So an absolute value equation includes the absolute value of an expression involving a variable. For example, x plus 2, the absolute value of that is equal to 6. To solve, you can graph the left side and graph the right side, and then the points where they overlap are the solutions. So the points of intersection are when x equals -8 and when x equals 4. So we're looking at the x values of those points of intersection. Okay, so that's graphically, and graphically is pretty easy. The algebraically has a little twist to it. We consider two separate cases. We first of all say, well, inside those absolutes, it's greater than 0, so we take it as it is. It's case 1. Case 2, we take what's inside the absolute values and we put a negative on it, and we solve for that. The last thing we have to do is we have to verify by putting back in. Something to watch for, if they ever tell you the absolute value of something is -7, can't exist. The absolute value of something can never be a negative answer. So they might try and trick you in that way. Okay, so let's give this a try. X plus 3 is equal to 8. So let's do algebraically. So first, let's say x plus 3 is greater than or equal to 0. So this is the easy part. We just say x plus 3 equals 8. We say x equals 8 minus 3, x equals 5. Okay, now let's say x plus 3 is less than 0. So if it's less than 0, then we know negative x plus 3 is going to equal 8. Because if we had a negative number in there, it would then become positive. Okay, so now we go negative x minus 3 is equal to 8. Negative x is equal to 8 plus 3 is 11. X is equal to negative 11. Okay, so and now I'll show you what that looks like if we were to graph it. So x plus 3 equals 8. And I have a graphing calculator, and you can do this on the iPads. We go the absolute value of x plus 3 equals 8. And we look at the solution. So it looks like we have one solution at 11, at negative 11 right there. And we have another solution, and that looks to be at 4.5, 5 at 5. Did we get 5 and 11? I have a bad memory today. 5 and negative 11. Perfect. Okay, I'll do one more example. Solve the absolute value of 3x plus 2 is equal to 4x plus 5. So we'll do algebraically first. So first we're going to pretend that this is positive. 3x plus 2 is greater than or equal to 0. So then we just take it as it is. Okay, we're going to bring all the x's over to this side. 4x minus 3x is just 1x. We're going to bring the 5 over. 2 minus 5 is negative 3. Okay, so we have x equals negative 3. Let's say 3x plus 2 is less than 0, so we're going to put a negative in front. 3x plus 2 is equal to 4x plus 5. Distributing the negative, 3x minus 2 is equal to 4x plus 5. Let's bring them all over here. All the x's over there. Let's bring the 5's over. In this case, we'd have negative 7, so x equals negative 1. Okay, let's just double check that both of these works. Let's sub in the negative 3. Does 3 times negative 3 plus 2, the absolute value of that, equal to 4 times negative 3 plus 5? Let's check this out. Well, 3 times 3 is negative 9 plus 2. 4 times negative 3 is negative 12. Okay. Negative 9 plus 2 is negative 7. Does the absolute value of negative 7 equal to negative 7? The absolute value of negative 7 is 7. Uh-oh. Those do not equal. This is an extraneous root. Doesn't work. Okay, let's try this negative one. Let's make sure that works. So we have in the original equation 3 times x plus 2. The absolute value of that, does that equal 4 times negative 1 plus 5? So negative 3 plus 2, is that equal to negative 4 plus 5? Does the absolute value of negative 1 equal to 1? You better believe it does. So that solution works. Okay. 3x plus 2 and 4x plus 5. 3x plus 2, 4x plus 5. Let's graph this. 3x plus 2 and 4x plus 5. So let's look at where it intersected. You'll notice that there is actually only one intersection, and we did only find one, and that is exactly at -1. If I zoom in, we might be able to see that a little nicer. Okay, there you go.